Namaste. Namaste everyone. Welcome to Ray Optics class. We have been studying about refraction through curved surface, refraction through refraction through a lens maker's formula. When two thin lenses are kept in contact, what is the power of the combination? What do you mean by power? What is the SI unit of power? And you will be asked to write the definition of SI unit of power. SI unit of power is diopter, right? When you write the full diopter, you should use small letters, symbol capital letter. So power is 1 by F. Power is defined as the reciprocal of focal length. What do you mean by 1 diopter? 1 diopter, if power has to be 1 diopter, if focal length is 1 meter. Because if only focal length is in SI system, then power will be in SI system. Otherwise, you will have to write different unit of power. So if F equal 1 meter, then power is 1 diopter. So power is said to be 1 diopter if the focal length of the lens is 1 meter. So power of a lens of focal length 1 meter is called 1 diopter. If your lens is having a focal length of 1 meter, then its power is 1 diopter. Okay, now how these lenses will form the image? We will have to see the ray diagram for the formation of image in the case of lens in different positions. We have studied how the image is formed in a concave mirror at different positions of the object. Similarly, we have to see the image formation in a convex lens, and always try to compare concave mirror with convex lens and concave lens with the convex mirror. You know, convex mirror, which reflects from the outer edge, outer surface, always forms diminished virtual image. That's why it is used as a rear view mirror. It is the only type of image formation in a case of convex mirror. So it always forms diminished virtual erect image inside the mirror. Rear view mirror, you know it, right? Now what about the concave mirror, which reflects from inside part? It forms different types of images. If you can recall it, when the object is at infinity, image is at focus, because parallel rays come and get focused. When the object is beyond the center, that means double the focal length. When it is beyond the center, image is between F and C, focal length and focus and C, and the image is diminished, inverted and real. And when the object is at C, image is also at C, same size. When the object is between F and C, image goes to beyond C and it is enlarged. Whatever is beyond C is enlarged, whatever is between F and C is diminished. And when the object is at F, image is at infinity. When the object is brought within the focus, enlarged virtual image is formed within the mirror. So recall that part and be ready with your pen and paper. Let us draw the image formation in a convex lens at different cases. Convex lens behaves very similar to concave mirror. Only the thing is, in lens we have refraction, in a mirror we have reflection. That is the only difference. Okay, shall we start producing all the images here? We will see all the types of images formation. Now suppose you take a convex lens like this. In a convex lens, we don't have a common center. The centers of the two surfaces lie on either sides, whereas in a concave mirror there was a single concave surface here. So, and the center lies here. So center is at double the distance from the focus. So F and C, R is equal to 2F, we write. Such a formula doesn't exist here. It is not applicable to lenses. Lenses have two centers, the center of curvature of one surface, center of curvature of another surface. But if you want to analyze it with this concave mirror, comparing with concave mirror, we select this position as 2F, double the focal length. Such a type of position we indicate in a convex lens, whereas in a concave mirror we have center which is double the focal length, which is not found. That center of curvature will not be at the double the focal length. So we will take a lens, and you know, in a lens, if parallel rays are incident on the lens, paraxial rays which are very close to the principal axis and parallel to the principal axis, after refraction they meet at focus. And if you pass a ray of light through the focus, they become parallel. So if an object is kept at focus, the rays become parallel like this. And if the parallel rays are incident, they pass through focus. And another one is geometric center of a mirror lens is called optic center. The whole size or area available for refraction in a lens. Find out the midpoint of the total area, that is optic center. Any ray of light incident through the optic center, it gets displaced by a small amount like this. Actually it gets displaced like this. There is a lateral shift. It is acting like a glass slab. So this part of the lens can be taken as almost a glass slab, parallel sided glass slab. So there will be a small shift. But if the lens is very thin, what happens is, if the lens is very thin, you can take this almost straight. It's a very thin lens, and this displacement from the original direction to the final direction is very small. You can take it as almost a straight line. So any ray of light incident on the optic center, it passes undeviated like this. Without any deviation, it moves out. So these are the things we have to consider while forming the image here. So let us take a convex lens first. So we will divide the positions. First condition, object at infinity. Okay, object at infinity. And it's easy to draw that now, since you have already studied concave mirror, so it is very easily understood. Take a concave lens and mark its focus, and it will have two foci. If you incident parallel rays here, they will get focused here. If you incident the same parallel rays from this side, so they get focused here. Whatever be the radii of curvature of the two surfaces, focal length will be same on either sides. That cannot be different. Focus here is at it far away, or focus here nearer is not possible. Focal length is always same on either sides. So if you take like this, and if this is 2f and if this is 2f, double the focal length. There is nothing like center. Center of this surface may not be at 2f. For a lens it is not possible. Similarly, center of this surface somewhere else, not at 2f. Now, what do you mean by object at infinity? At a very far away distance. Compared to the size of the lens, object is at far away distance. So you can take parallel rays of light like this. So when parallel rays of light are incident on a lens, they are coming from infinity. So from infinity, this is from infinity because very far away, and they meet at focus. So how do you describe this image? This image is highly diminished. It's a very, very small image. So you might have used this experiment, you might have done this. You are using a small convex lens, magnifying lens, and holding a paper here, holding this against sunlight. All the sunlight gets focused onto the paper, and after some time the paper will start burning. All the rays, all the radiation, when it is focused at a point, it gets heated and it starts burning. Same experiment. What do you get? What do you see here? The point, very bright point object. What is it actually? It is nothing but the image of the sun. So image of the sun is highly diminished, very small, real and inverted. So I can write the image as highly diminished, real, inverted image is formed, inverted image at focus. So when the object is at infinity, object at infinity, and image is highly diminished, real, inverted image at f is formed. This is one case. Shall we take the opposite case of this? We will keep the object at the focus. Take a bulb and keep it at the focus. What will be the condition? You take a bulb, keep it at the focus. So now the bulb is at the focus. All the rays of light coming from the bulb will be coming from the focus now. They become parallel after refraction. So there is no reflection here, only refraction. So if the object is at focus, object at f. What about image? Image at infinity. Image is at infinity, and what type of image? And these rays may meet at a very, very large distance, and they will form highly enlarged, real inverted image. right? So it is a quite opposite case of this. When the object is at focus, the rays which are coming from the object become parallel after refraction. It is the quite opposite of this, and they meet at infinity, producing a highly enlarged real inverted image. Okay, now we will come to 2f. Beyond 2f, not at infinity, at a limited distance away from 2f. Okay, object at away from 2f. So I will keep a lens here, convex lens, right? So like this. This is f, this is 2f, and here is f, here is 2f. Keep an object beyond 2f. Okay, you know that anything beyond c or beyond 2f is larger, so let us take a larger object so that it becomes easier to analyze. So beyond 2f, this is larger. Consider two rays of light. One ray of light passing parallel to the principal axis, after refraction passes through focus, and another ray of light passing through the optic center meets this ray here. Is it okay? So you have to consider two rays of light. So you should have arrow mark. After refraction you should have arrow mark. Of course it is here, this one. So that is how it moves. One ray of light parallel to the principal axis after refraction passes through focus, and another ray of light passing through the optic center, it passes undeviated. There may be small displacement. Since this lens is very thin, you can say almost it passes without any bending. They meet here. What is this? This is inverted image. If this is A and this is B, then A dash B dash, or this is A and this is B, this is B dash A dash. B dash A dash is the image. So object beyond 2f. Where is image? Image is real, inverted, diminished, small sized. Real, inverted and diminished. That is one part. Okay. Now take another case, opposite case of this. Let the object be between f and 2f. It is opposite case of this. So you can remember the whole table like this, right? So quite opposite cases must be understood very easily. Object at infinity, image at focus. Object at focus, image at infinity. Object beyond 2f, image is between f and 2f. Now the object between f and 2f. If it is between f and 2f, it is smaller. Beyond 2f will be larger. So image goes beyond 2f. So I will take one lens, and here is f, here is 2f, and here is f, here is 2f. Let the object be kept between f and 2f, and this is B and this is A ray of light incident parallel to the principal axis after refraction passes through focus, two arrows, and another ray of light passing through the optic center. Okay, this is not up to the scale now. You have to do something here. You should get an image beyond 2f, right? So f, 2f, and I think I have selected, okay, here like this. So here should be f, somewhat same distance, f, and here should be 2f, yes. One ray going like this, and another ray, another ray going like this and meeting beyond 2f, yes. This is f, I will shift it here, and this is 2f. So the two rays meet here after refraction, and this is B dash A dash. So object between, this is object between f and 2f. What is image? Image is here. Image is enlarged because it is away from 2f, enlarged, real, inverted, enlarged, image is enlarged, real, inverted, and between f and 2f. Sorry, beyond 2f. Beyond 2f. So if you observe here, object is beyond 2f. This is between f and 2f. Here in this case, here it is beyond 2f. So when the object is between f and 2f, an image enlarged in real and inverted is formed beyond 2f. Okay, now we will come to 2f. At C, concave mirror, remember, it is at C. Same sized image is formed at C. But here in the concave mirror, it is formed at the same place, but here on the other side. So at 2f, shall we go to that? At 2f. At 2f. Object. So take a concave mirror, a convex lens. This is f, and I'll write it later. This is 2f, and this is f, and this is 2f. Okay, I will have to change this to f later. So this is one object, and I'll call this as AB, and a parallel ray parallel to the principal axis. After refraction passes through focus, and another ray passing through the optic center. It has to move such that, okay, I'll have to move it in such a way that it an image is formed at 2f itself. It is not proper now, right? So I'll have to shift this. F is somewhere here, then yes, now it is okay. So if f is here, then this ray parallel to the principal axis after refraction passes through focus, and another ray passing through the optic center moves here, and I'll call this as 2f, and it is almost of same size as this one, right? And this is B dash, A dash, and image is formed at 2f only. So at 2f, object at 2f, then image is also at 2f, right? Image at 2f, right? Image is at 2f, and inverted, real, and same sized. So I can go through this a little bit faster because already we have seen it in the case of a concave mirror, you know it. Okay, so same sized, inverted, and real image is formed, and it is also at 2f. Now comes the special case. You know that when the object is within the focus in a concave mirror, we see the enlarged image inside the mirror. That's why it is used by dentists. It is a dentist mirror. Similarly, do we have such application for convex lens? Yes, we have an application for convex lens when an object is placed within the focus of a convex lens. Now this is very important. When an object is placed within the focus of a convex lens, I'll keep an object here. What will happen now? That is more interesting now. I'll rub this for the timing. Yes. Yes. Now, focus is found on the other side also, 2f on the other side also. 2f, f. You consider a ray of light parallel to the principal axis, like this. And it passes through the focus. And another ray of light passing through the optic center, it moves like this. And these two rays never meet each other. I will have to change a little because I don't use any scale. I'm drawing everything along approximate distances. So this is f, this is 2f, and this ray of light is moving like this. And this is the parallel ray incident on the lens, it is moving like this, and this is through the optic center moving like this, and these two rays never meet. They never meet, they diverge. Suppose you try to get an image here, for a person observing from here, can you see the image? He feels that these two rays, they appear to come from a point here, this ray and this ray. And these rays appear to come from a point here if they are produced backwards. So this is not a real image, this is a virtual image. So shall I call this as B, this one A, this is A dash, this is B dash. So if the object is kept within the focus, object within F, image is formed same side, on the same side as the object. Image is virtual, erect, enlarged. Virtual, erect and enlarged, formed on the same side, right? Formed on the same side as object. Same side as object. Now, this is the special case of a convex lens. If an object is held within the focus and optic center F and O of a convex lens, then the virtual, erect and enlarged image, so this is of more importance to me, enlarged, virtual, erect and enlarged. You need not have to have a separate screen to catch it. You can just see, if you observe it here, these diverging rays will never meet and they appear to come from this point. So you see the enlarged image of this object. That is what we see, what we do while using a magnifier lens. We hold the lens in such a way that we get the enlarged image. We adjust the lens till the object comes within the focus. As soon as the object is within the focus, we get an enlarged image, and that is a simple microscope. So this is the diagram for simple microscope. Simple microscope uses one convex lens. This is a simple microscope. It uses one convex lens and the object must lie within the focus. So if you are asked to draw the ray diagram for the image formation in the case of convex lens for virtual image, this is the only case. For all the other cases, image is real. The rays really meet after refraction, correct? So in all the other cases, really they meet after refraction. Whereas here, they don't meet. They appear to come from a point. This is virtual. This is the only virtual image formation case, and only virtual image formed by a convex lens is enlarged. So that's why it is used as a magnifier. Just adjust the reading lens such that you will get enlarged image inside the lens itself in the same side as the object is present. That is why it is called a simple microscope. Whereas this application is in the case of a concave mirror, it is as a dentist mirror to see the enlarged image of the teeth. Okay, so this is the various image formation in the case of convex lens. Now let us have simple problems regarding this. Of course, I will take some example and I will go on solving this. Now this part of the this one you need not take it, because when the object is at infinity, image is at focus. When the object is at focus, image at infinity, that part is not needed. We will take it from here. And what is lens formula? I am not asking you lens maker's formula. I am asking you lens formula. What is lens formula? Lens formula is nothing but 1 by f equal to 1 by v minus 1 by u. This is lens formula. And what is magnification? H dash by h is equal to v by u. That's all. No negatives here, only negatives here. Whereas in mirror formula, h dash by h is equal to minus v by u. And here there is no negative. 1 by f equal to 1 by v plus 1 by u. In mirror formula. This is lens formula now. Now let us take this case when the object is beyond 2f. Now let us take a convex lens. We will consider a convex lens of focal length is equal to say 6 meters, and an object is kept at a distance of object distance is equal to, if focal length is 6 meters, 2f is 12, let me keep it at 18 meters from the lens. Now where is the image and what type of image? Shall we apply? So a convex lens of focal length 6 meters is kept in front of an object at a distance of 18 meters. Where will be the image formed? Where you will have to keep the screen? Definitely it will be between f and 2f, right? So when the object is beyond 2f, image is between f and 2f. So our image distance should be between 6 and 12. Image distance should be between 6 and 12, any number between 6 and 12, and image is inverted and image is on the other side. So if I put the this coordinate diagram like this from the optic center, all the distances are measured from the optic center now, not the pole. There is no pole. Optic center. Distances measured in this direction are negative, in this direction are positive. So what the image distance that you get finally should be positive. So we should get image distance positive, and magnification will be negative, and because image distance is measured from the optic center in the direction of incident light, whereas this object distance is negative, because when you start from here, when you move this direction to measure the object distance, you are going against the direction of incident light. It is negative. Okay, shall we do that now? So U is minus 18 meters. V is question mark, of course we have here. And focal length, sir, what should we do the focal length? From the left side, you incident parallel rays, they meet at focus. Focal length is on the right hand side. It is plus 6 meter. So what is the formula? 1 by F is equal to 1 by V minus 1 by U. That implies 1 by F, 1 by 6 is equal to 1 by V, don't know, minus 1 by U. U is minus 18, this side. Minus 18. This becomes plus 18. 1 by plus 18, or I will write the step. 1 by 6 is equal to 1 by V plus 1 by 18. That implies, bring this 1 by 18 here. 1 by 6 minus 1 by 18. This part here is equal to 1 by V. Take the common denominator. 18. 6 3s are 3. 18 1s are 1. That is equal to 1 by V. That implies 1 by V is equal to 2 by 18, that is 1 by 9. What is V? V is equal to 9 meters, and we got it as plus 9 meter. Is the answer correct? Yes, it lies between 6 and 12, right? Focal length is 6 and double the focal length is 12. This one, 9 comes somewhere in between, and it is positive on the other side, so answer is correct. So that is why this formula is suitable for all the forms of images, but you have to apply the sign convention again and again. So this is 9 meters. So that is the beauty of this one. Now we will take the reverse case. Suppose this is the case now. I'll rub this now. This is not needed. Object kept between F and 2F. Image is beyond 2F. Let me take a different convex lens now. Let us not stick on to the same answer. Of course, if you keep the object distance at 9 meters, or you can take it this one itself. Now let me keep an object between F and 2F. Yes, 9 meters. So I have a convex lens of focal length 6 meters, and object is kept at a distance of 9 meters. I will give positive and negative signs later. Where is the image formed? Of course. And here you see, coming back to the previous problem, one thing I have forgotten. Image is, so object is beyond 2F, image is between F and 2F, it is diminished. Anything between F and 2F is diminished. How do you prove that? M is equal to V by U, that is equal to image distance 9, U object distance, that was minus 18, that is equal to minus half. Am I right? Minus half means minus 0.5. What is the meaning of 0.5 and minus 0.5? Minus indicates that image is inverted. It was beyond 2F, sorry, between F and 2F, and 0.5 indicates that image is diminished. It is half of the size of the object. Now coming back to this problem. Focal length is 6 meter. Object is kept between 6 and 12, that is 9 meters. And where is the image distance? So if I can draw it like this, simply this is 6 meters and this is 12 meters, this is 2F, this is F, and object is here at 9 meters. And image should be formed somewhere here. You know that when the object is between F and 2F, image is beyond 2F. That means your answer should be beyond 24. This should be greater than 24, right? Greater than 24. Not 24, sorry, 12 meters, because focal length is 6 and 2F is more than, so 2F is at 12, image distance should be at a distance more than 12 meters. Shall we get it? We will check it. 1 by F equal to 1 by V minus 1 by U. That implies 1 by 6 focal length, positive focal length. Why? Because if you incident parallel rays, they meet at the focus. On the other side, positive, is equal to 1 by V, don't know, minus 1 by U. U is minus 9, right? and this is plus 1 by 9. When you bring it here, that becomes 1 by 6 minus 1 by 9. Minus minus becomes plus. Here it becomes negative 1 by v. So shall I take 9 as common? And if I take 9 as common, no, not 9 as common, it is 18 as common. I can take 18 common, 3s are minus 2s are, 9 2s are is equal to 1 by v. That implies 1 by 18 is equal to 1 by v. V is equal to 18 meters. Is it greater than 12? Exactly. And plus, what is plus on the other side? It is formed on the right side of the lens. It is sure 2f lies away from this. Okay, so this part is proved now. What about the at 2f, at 2f? We will take that case. That's a beautiful case. When the object is at 2f, image is also formed at 2f, and image is of the same size. Okay? Right. Now, okay. Right. I will take an object, lens of focal length 6 meters, and object at a distance of 12 meters, and where is the image? Let me do it like this. 1 by f equal to 1 by v minus 1 by u. You should get v as 12 and positive on the other side. U is minus 12 because it is on the left hand side. I need not draw it again and again and show it because that's a repetition. 1 by 6 is equal to 1 by v, don't know, minus 1 by u minus 12. So shall I write it as plus? 1 by 6 minus 1 by 12 is equal to 1 by v. What does it indicate? 12, 6 2s are, and 12 1s are, minus 1 equal to 1 by v. That implies v is equal to 12 meters because this is 1 by 12 and 1 by 12 is 1 by v. V is equal to 12 meters, which is same as u. So when object is kept at 2f, image is also at 2f, and on the other side plus, object is in this side minus. Now we will see this case, enlarged virtual image when the object is within f, that particular case. Take a lens of focal length say 6 meters positive on the other side. Parallel rays meet here, and let us keep an object within the focus, say 3 meters, and it is minus, you know that. So when the focus is here, when the object is here, this is 3 meters and this is 6 meters, and this is negative because on this side, where is the image? Now the image distance should be negative because you should get an image on the same side as the lens. Now for the first time we are getting image distance as negative. Is it so? We will do that. 1 by f is equal to 1 by v minus 1 by u. Okay, 1 by f, 1 by 6 positive is equal to 1 by v, 1 by v. What is 1 by v? No, don't know. Minus 1 by u, u is minus 3. And 1 by 6 is equal to 1 by v plus 1 by 3. 1 by 6 minus 1 by 3 is equal to 1 by v. That implies I can take 6 as common. 6 1s are, 3 2s are, 1 by v. This is minus 1 by 6. So v is 1 by v is equal to minus 1 by 6, and v is equal to minus 6 meters. What do you mean by minus 6 meters? Image is formed on the same side, that is left side. You have to come from the, because the rays of light are going like this. You have to measure the distance from the left towards the left, that is opposite to the incident light. The image is formed here. Is it enlarged? Magnification greater than 1? Greater than 1 in the sense its value is greater than 1, the magnitude, then h dash by h. Okay, v by u. What is v by u? V is minus 6, u is minus 3, so you get 2 answer. What do you mean by magnification 2? Image is double the size of the object and it is plus 2. What does it mean? Plus 2 indicates that it is above the principal axis. So everything is crystal clear. Only the thing is you must have everything in your brain, and you should keep on executing it one by one. So magnification is plus 2, double the size, and it is plus means it is above the principal axis. So everything is dealt. Now we will move on to concave lens. Hope we will get enough time to do that. So concave lens always forms virtual diminished image. It is the only virtual diminished image. It is the only case that you get in a concave lens. So concave lens forms virtual diminished image as similar to a convex mirror. Convex mirror always forms virtual diminished image wherever is the object. Now we will take a concave lens like this, and it will have a focus, and so wherever you keep an object, let me keep an object here. It's a diverging lens, you know that. Here you should be very careful while you draw the diagram, because we have been addicted with all those rays of light. Parallel ray passes through focus, another optic center passes undeviated. But here you should be very careful. A parallel ray, it doesn't converge, it diverges. How does it diverge? What you have to do is you have to keep a scale here, then diverge it like this. Don't diverge it anywhere and try to meet at focus, right? Try to bring it to focus. Diverge it in such a way that it comes from focus. Another ray of light coming from A only. So A, B. It passes through the optic center without bending. Have you observed the two rays? One ray parallel to the principal axis, after diverging it appears to come from focus. So for a concave lens, if parallel rays are incident on the concave lens, they diverge in such a way that they appear to come from focus. They don't meet at focus. They appear to diverge from the focus. Focus comes to this side, it is negative for a concave lens. So focus comes to the left hand side. So you have to consider two rays of light. One ray parallel to the principal axis diverges such that it comes from focus. Don't simply draw lines like this and try to put it into the focus. It becomes odd. So try to keep a scale here, then produce it like this. Next, another ray passing through the optic center, and it passes undeviated. Any person observing these two rays from here, he feels that this ray is coming from here and this ray is coming from here. He feels that the two rays are coming from here, so he feels that the image is here. This is A dash, this is B dash. So for any position of the object, image is virtual, diminished, and erect. Virtual diminished erect image is formed on the same side, right? On the same side as object. This is the type of image in the case of concave lens. This is the only case, right? And you don't have any other case at all. Wherever you keep the object, it always forms virtual diminished and erect image, right? Virtual diminished erect image on the same side as the object, and this is the speciality. And all these ray diagrams must be very clear to you, because using the ray diagrams you might be able to solve the problems, because all these ideas sometimes give you where the object is. Because in entrance examinations you will get problems where two lenses, one mirror and the plane mirror, so many things are combined. You must be aware of all the rays of light, right? Now if you want to work out problems, do we have time? Okay, we will work out one problem now. Yes. A lens, concave lens of focal length is equal to, okay, we will take the same data, 6 meter. An object is kept at a distance of say object distance is equal to some okay, we will take it as 18 meters, same thing, from the concave lens. Now what is the image distance? Where is the image? Formula is same, 1 by f is equal to 1 by v minus 1 by u. It is universal formula, no problem at all. For any lens you can apply. But only the thing is, now focal length is negative. Do you know why it is? If you incident parallel rays, they diverge in such a way that focus comes to the left. It is minus 6. Object distance is minus, it is in the left side. So now apply this. What is the position of the image? You should get it on the left side, and image distance should be smaller than 18. Why? Because it is diminished. So V by U should be less than 1. So what is the answer now? That implies 1 by F, 1 by minus 6 is equal to 1 by V, image distance. Where is the image distance? That has to be found out. Minus 1 by U. U is 18 minus 18. So what you are left with now? 1 by minus 6 is equal to 1 by V plus 1 by 18. That implies, I will bring this 1 by 18 here. Minus 1 by 6 minus 1 by 18 is equal to 1 by V. Where shall I write it now? Shall I raise it here? I will put it here. Right? Now 18 common, 6 3s are minus 3 minus 18 1s are minus 1. That is equal to 1 by V. Minus 3 minus 1, minus 4 by 18. Is it correct? Minus 1 by 6, minus 1 by 18, 18 common, 18 6 3s are, and 18 1s are. Minus 4 by 18 is equal to V. What does V imply? V equal to 18, okay. That is 1 by V, right? Minus 4 by 18 is 1 by V. What is V equal to? Minus 18 by 4, that is 4s are, minus answer. 4s are and 0.5. Minus 4.5 meter, that means towards this side. And it is less than object distance. So if you try to find out the magnification, magnification is equal to V by U. V is minus 4.5 divided by 18, and the magnitude of this is less than 1, right? That means it is diminished. And it is, okay, minus, this is also minus. Minus 4.5 by minus 18, because image is in this position, object is also in this position. Of course, it is less than 1, and it is positive. Finally, magnification is positive. What do you mean by that? Image is erect, on the, it is above the principal axis, but answer is less than 1, it is diminished. So this is how you can form the image formation. This is very easy since we have studied concave mirror and convex mirror. Just compare the tables of concave and convex mirror, you will come to know what happens, right? And it is an identical, and all the table becomes easier once you know all these things. And better you finish all the problems related to this, directly finding the size of the image and size of the object, or image distance and object distance. So with this introduction, we will move on to the problems. We will meet in the next class. Keep all these things in your brain. We will meet after in the next class. So till then, keep studying and remember all the formulas. All the best. Thank you.